Okay, so in this lecture what we're going to do is give you an overview again of the weak form, starting with a strong form ODE, and then we'll put it in the weak form or integral form, and at that point we'll take one more step and talk specifically about interpolation functions. And in this case, for a linear second order ODE, we show that you need at least a linear polynomial for the interpolation function. So recall, for these second order ODE problems in 1D, one form of the ODE is this form. So we have this strong form equation over a distance of coordinate x from 0 to L. And one example of boundary conditions would be to define the dependent variable solution. This may be temperature, it could be displacement, depending on the physics of the problem. And then on the other end, or x equals L, you have the gradient of your dependent variable times some material parameter, and this is your flux or load on that end. Also note, this table refers to Reddy's book. It gives a pretty good summary of the steps in formulating the finite element problem, starting with the ODE, putting it in a weak form, and I believe discretization. We'll talk about it more in class, but I think it gives a pretty good description on all the key steps required to set up this problem. So again, a few physical examples. You may have temperature or displacement on this one end. We're defining displacement as U naught or T naught. You could have these internal fields or gravity as a body load. It could be a centripetal force, such as a helicopter rotor blade. And then on the opposite end, you may have a load P, or you may have heat flux. You may also have convection. So remember earlier we talked about heat transfer problems where you may have convection internally over the perimeter of a bar. So our model for this is just a one-dimensional line along X given L length. These internal fields or gravitational loads and boundary conditions on each side. So thus far we've primarily talked about a single finite element. So you have some known solution on the endpoints. But there may be these cases where you have these internal variations. You notice this is a function of x. So this doesn't have to be a constant gravitational load. It could have some unusual characteristics, particularly if it's something like convection. Convection cooling may vary along the length, so then you may have these variations, and then you may not be able to approximate this by one big element. So what we're showing here is we're dividing this bar up into multiple elements, or in other words, finite a set of elements of finite length h sub e. So we'll talk later about what it takes to first construct the matrix set of equations for one of these elements, and then once you have that, you can do that for every one of these and then put them all together so you have continuity. Remember, we have things like continuity and displacement. Unless this fractures at, say, node 5, the displacement has to be continuous. Similar things have to happen with temperature. Temperature has to be continuous across a node. So we use those physical constructs to put this set of finite elements into a matrix set of equations that we can solve on a computer. Alright, so recall, here's our strong form. We want to put this into a weak or integral form, and then that'll lead to a way to discretize it, or in other words, put it in a matrix. So we put an integral around this, it looks like one thing that's missing is we should multiply it by a weight function, so there should be a W out here. And if you go back and look in your notes, we used integration by parts or product rule, and we got the problem down to this integrand. Here's your weight function, here's your dependent variable, let's say displacement or temperature, mixed combination of material parameters, weight function, U, same thing here, and then here's your boundary conditions on the end. Now notice we're going from XA to XB. So this is some arbitrary element inside the bar. So you're going to have other elements out here and also out here. First, we just want to focus on this one single element. So a little bit of notation. We have what's called flux boundary condition. That's defined here. So here's our fluxes on the ends of XA and XB. These are also called natural boundary conditions. So you'll hear me say this quite a bit. Anytime we're talking about a flux on the ends or on the nodal points, this is a natural boundary condition. Conversely, your essential boundary conditions are the dependent variable solutions. So either your displacement or temperature in these cases we've been discussing. Alright, so substituting in this definition of flux, you have these values at the endpoints, and then we have to figure out how to evaluate this integral. So we're going to approximate it. And we're going to assume that we may not be able to get the exact solution, U, but we may be able to get something close to it. So this nodal approximation. And we're going to say that that nodal approximation is equal to a summation of some functions, and you may have one at, for phi naught. These may be summed over j equals 1 to some unknown value. We'll specify that in a moment. So for the weak form, we want to first start out with the minimum polynomial estimate for U. And in this problem, that means it's a linear polynomial. So you have two unknown constants, C1 and C2. Superscripts stands for a single element. Okay, so what we must satisfy is some nodal solution at the endpoints, XA and XB. So at XA, you just have these constants. You plug in XA for our function of X, and that's equal to that nodal solution at the end. It's some unknown value, but we have some finite element solution. Same thing at the other end, you just have XB here. So you can put these two equations into a matrix, and what we don't know are these constants C1 and C2. We're assuming that these will be known from the finite element problem. Okay, so you want to solve for these, and you can invert this, and what's left is C1 and C2 as a function of the length, the nodal solutions U, and your coordinates XA and XB. So in Reddy's book, he introduces this notation. So this is your interpolation function, phi sub j, and now we have these nodal solutions, U sub j, for each element E. So based on this process of inverting and solving for this, it turns out here is your finite element interpolation functions. So for this simple case, j equals 1 to 2, we have two interpolation functions, or you can also call these either interpolation functions or weight functions if it's a Galerkin method. But anyway, we sum this over 1 and 2 by just using this equation. And you'll notice these functions have interesting properties. So at the endpoints, phi2 is 1, the other endpoint is 0, and conversely this one is 1 at XA and 0 at XB. So this always holds for these finite element problems. doesn't even have to be just a linear interpolation function. It can be higher order. This will always hold. Okay, and also, so at these endpoints, it's 0 or 1, and then if you sum it anywhere on the domain, any point within X over that element, it's always going to be 1. Now, often what we'll do is we'll use these normalized versions. And I think, yeah, we'll stop right here, but I'll talk later about what I mean by this normalized value. That will become very useful when we assemble these elements into a large array of chains. Remember earlier I showed, where is it? Yeah, right here. So we'll make a correlation between the global coordinate x and a local coordinate x bar, so we can figure out how to assemble these.